So in today's session, we shall be covering probability distributions. We expect to take around 3 to 4 classes covering this entire chapter. So compared to all other chapters in CS1, the number of classes, at least for paper A part, is gonna be slightly, more for this particular chapter. And the reason for that is that whatever we are gonna study in this particular chapter is gonna set the base for the entire paper. Ultimately, our main emphasis will be on the various distributions. So it's important that you all do get comfortable with the various distributions commonly tested across CS1, the various properties they possess, and so on. So in the random variable, which was the fourth prerequisite class, you might have covered, we have either a discrete random variable or a continuous random variable. Then we had something called a PDF. We were calculating, let's say, the CDF, mean, variance, skewness, etc. So what we do in probability distributions is, for a given specific PDF, we have given the name to a particular distribution. There are certain commonly used distributions, be it with respect to insurance company or any other statistical applications. So we are gonna cover those in a lot of detail. So again, here we have two sort of distributions. We would be looking at the discrete distributions, which is the intention of today's session. And going further, we shall be covering the continuous distributions as well. Keep in mind, we have several discrete distributions, not the ones which we are covering in today's session are exhaustive in nature, but for the purpose of, let's say, the actuarial syllabus, specifically CS1, these are the things, which are going to be required. More, you could find more distributions if you try to Google it out, or, in certain past questions, they might have come up with another distribution. So we are going to focus on the most commonly used standard discrete distributions in today's class. Keep in mind one thing, we will try to understand intuitively, specifically for discrete distributions, as to where we can apply it on our day-to-day life basis. For continuous distribution, see in examination, they would be mentioning, which continuous distribution to use. But for discrete distribution, it is not necessary that the question will be explicitly stating the distribution to be used. We could use any distribution, when I say any, in the sense that they might have expressed in words. From that, we need to apply logic to see which particular discrete distribution is the correct one to be used in that particular scenario. So I would be noting now the distributions which we would be looking in detail. So we would be starting from uniform. Then we would look at something called a Bernoulli. Then we will look at something called a geometric, which we will see will have two types. One will be type 1 and another will be type 2. Then we will be looking at binomial. Then we will be looking at negative binomial. Again, this has two types, type 1 and type 2. Then we would be looking at Poisson distribution, which would be one of the most important distributions. And ultimately, we would be looking at hypergeometric. The last one will be a relatively shorter one, something which is not frequently used for our analysis at least. So what we are going to study about this is, first of all, the structure, that is, let's say, the probability function for all these distributions. We would take a look at, calculating mean and variance for quite a few of them. And, just to get comfortable, what sort of mathematical manipulation or steps are required, when you are calculating any sort of expectation, be it mean, expectation, expert, so on, for a particular distribution. Each distribution, will bring in itself a different technique to go about solving it. So we would be doing that. Keep in mind the mean, the results for the probability function, mean, variance, and even few other quantities are there given in actuarial tables. So there is no specific need for you all to memorize it, be it whether you're appearing from II or whether you're appearing from IFOA. All these are given in actuarial tables. Our focus would be to understand where these distributions could be used, and as well as the mathematical techniques required to deal with these particular distributions, be it for expectations or any other calculation of any other expectation, whether it's mean or whether it's some higher order expectation as well. And we will also try to see among these which all distributions are related to each other. Can I start from one, go on to the other, and so on. So first, give the heading uniform discrete distribution. We would be looking at uniform distribution in continuous as well. So that is why, just to explicitly elaborate, the first distribution which we would be covering today is the uniform discrete distribution. Now, to understand this distribution, it's a very basic distribution. Uh, so here, let's say there are k different values, k different values which my random variable can take, and all of these are equally likely in nature. Under this scenario, we can use a discrete distribution. So my structure, let's say how I can go about writing this is, let me compare directly from how it's represented in actual tables so that you all will be able to appreciate. I hope the screen is visible to all of you. Here we have a discrete uniform distribution. Three parameters have been given: A, B, and H. Now, if you will see, this PF is nothing but the probability function which we have, and the probability function is given as H divided by B minus A plus H. Note that A, B, H all are constants only. So this probability is constant only. Whatever be the value of X, the probability will be taking the same value only. And what are the possible values of X given over here? A plus H, A plus 2H, and so on. So this is the format in which they have given the uniform distribution. Generally, a common way is, we just assume H to be 1 itself. So this will simplify to, let's say, X takes the value A plus 1, A plus 2, so on till the value B. So there are various examples. The generic form we have already done. Let me take a specific example where, let's say, probability X equal to X is equal to 1 by K, where my X can take the values 1, 2, 3 till K. So here try to see the random variables can take the value 1, 2, 3, so on till K. So the probability will be nothing but 1 by K. If you want to relate this to what we have in actuarial tables, if you will compare, then my A will be 1 starting value, my B, which is the ending value, will be K, and then H will be nothing but 1. And now if we'll try to relate to the probability function, H is 1, so in numerator we have a 1 over here. Then B is nothing but A is nothing but 1, H is nothing but 1. So what we are left with is nothing but 1 by K only. Again, range will be 1, comma 1 plus 1, which is 2, comma 3, so on till K itself. So this was the usual way, the way in which they are given in actual tables. This is another way where X can take the values, say between 1, 2, 3, and so on till K itself. Keep in mind, yeah, so these are the values basically which we are looking at. Now, first let us try to find its mean and variance, and then post we have done that, I will tell you under which scenarios we should be using this distribution. Even if it's not mentioned in the question, then under what circumstances should we be using this particular distribution. So first thing which we'll try to do is calculate expectation X, which from first principles will be nothing but summation X into probability X equal to X, where X is taking the value from 1 till K. So this will become summation x by k, x running from 1 to k. Now this summation is against x. So we can take the k outside. This will be 1 by k summation x, x running from 1 to k. Now try to appreciate and familiarize yourself to dealing with the summation and all. We have summation x, x running from 1 to k. This, if you want to expand it, will be nothing but 1 by k, and this will be 1 plus 2 plus 3 so on till k. Now if you would recall, the summation of the first k natural numbers is nothing but k into k plus 1 by 2. So this will be k into k plus 1 by 2, and what we are left with is k plus 1 by 2. Alternatively, you can directly use this result, and that is something which I would be suggesting. Summation x, x running from 1 to k is nothing but k into k plus 1 by 2. Here it might be more easier for you to see that this is the addition of first k natural numbers. Similarly, familiarize yourself so that you become comfortable in interpreting this directly. Summation x, x running from 1 to k is nothing but basically the summation of first k natural numbers only, written in a very compact form. So this becomes my expectation x, this result, and again this is something which you'll be finding there in tables. It will be in the form of probably a, b and h. By substituting the values, you'll get in this particular format itself. So here what we are trying to explain is here we'll need to be using the properties, summation of first k natural numbers. Next we would be looking at the summation of the square of first k natural numbers, and so on. So give it a shot. Try to find expectation x square. Give it a shot, all of you yourself. Try to find expectation x square. So you can take a look. The form which is coming is nothing but summation of the first square of the k natural numbers, the result of which I hope you will recall, k into k plus 1 into 2k plus 1 whole divided by 6. So simplifying this, expectation x square is coming out to be k plus 1 into 2k plus 1 whole divided by 6. And now if you will remember, if I need to find variance, the formula for variance was nothing but expectation of x square minus expectation x whole square. So this will be k plus 1, 2k plus 1 by 6 minus k plus 1 whole square by 2. I can take a k plus 1 by 2 common and I'll be left with 2k plus 1 by 3 minus k plus 1 by 2. This will be k plus 1 by 2. Here this becomes 4k plus 2 minus 3k minus 3 by 6. On simplifying, this will come out to be k plus 1 by 2 into k minus 1 by 6, which can be written as k square minus 1 by 12. So there we get the result. Now coming to where do you need to apply uniform discrete distribution? First of all, whenever you're modeling anything, say for example, if I tell you that I roll a particular die, unbiased die. So I can get either a 1 or a 2 or a 3 or a 4 or a 5 or a 6. And because I have mentioned that it's an unbiased die, probability of all of these would be nothing but 1 by 6 only. So here I can use a uniform distribution. So any scenario where whatever outcomes are there are going to be equally likely, I can use what? A uniform distribution. Just you have to keep one thing in mind directly, that the values which x can take must not be, let's say, 0. If you will closely take a look, want to directly deal with something. Here in the numerator I have an h. Okay. If my starting point is 0, well, yeah, we could actually deal with that, not an issue. My h, basically the increment should not be 0, and that makes sense as well. If h is 0, what it means is the values remain the same only, so there is no randomness over there only. So actually it can deal with all sort of values, whether we have negative range, positive range, negative values of x, positive values of x, so on. So remember, this application of a discrete uniform distribution is any scenario where all the possible outcomes are going to be equally likely, then you need to basically use the discrete uniform distribution. Next, what we would be looking at is the Bernoulli distribution. Next, we would be looking at Bernoulli distribution. So in a Bernoulli distribution, let us first take a look at structure, or the way to go about writing it. The way we write it is x follows Bernoulli P. This is nothing but what we basically say to be a squiggle. So the way to denote is x follows, or the way to read it out is x follows Bernoulli, where the parameter of interest is nothing but P. Keep in mind, when we were dealing with uniform discrete distribution, there were three parameters: A, starting point; B, ending point; and H, which is, let's say, the increment or the steps in which the random variable can take values. Here, the only parameter is nothing but a P over here. And you could write it down. The way to read this statement is x follows Bernoulli distribution with parameter P. So the probability function which we have for a Bernoulli variable is p to the power x into 1 minus p whole to the power 1 minus x, where this p we will look at is nothing but probability. So this value of p must lie between 0 and 1 itself. And the x can take only two values, either 0 or 1. So if I'll put x as 0, this can be simplified as probability x equal to 0. Probability of that is 1 minus p. Probability of x taking the value 1 is nothing but p. So when do we use Bernoulli distribution is in any particular scenario. Let's say there are only two possibilities. Then that can be modeled as a Bernoulli random variable. Let's say it could be anything, let's say gender. So I can, let's say, denote 0 when we have male, and if we have female, I can denote it to be 1. Then it can be, if you, let's say, anything where you can segregate into, let's say, either a success or a failure. For example, if you cleared the exam, then I will say it's equivalent to success, and if you fail, it's equivalent to a failure. So I will take the value 1 if you, clear the examination, and if you fail, then I will be taking the value 0. So for the application, any case where a particular, let's say, experiment or scenario can have only two possible outcomes, then I can model it as nothing but a Bernoulli random variable. So before going into Bernoulli distribution, let me also just make a note down what exactly is a Bernoulli trial. So just give a note in between and mention. A Bernoulli trial is an experiment. A Bernoulli trial is an experiment which has within brackets or can be regarded as having only two possible outcomes, or can be regarded as having is inside brackets. I'll just repeat again. A Bernoulli trial is an experiment which has within brackets or can be regarded as having brackets close only two possible outcomes. Give a dash and write success within brackets small s and failure within bracket f. So again, necessarily it does not need to be a success or a failure. As I said, anything which can take only two possible values. So for example, if I tell you that the color of the shirts which students are allowed to wear in a school is either white or say grey, then I can model this to be nothing but a Bernoulli, where I need to define, when does it take the value 1, which is treated as, let's say, success. If a student is wearing white colored, say, shirt or t-shirt, I will say this is a success. That is, my random variable should take 1, and it will take the value 0 when they are wearing a gray colored, let's say, shirt or a t-shirt. So here, in that case, x, I can define x under this scenario to be nothing but the number of success, and p is nothing but the probability of a success. Alternatively, p is nothing but the probability of x taking the value 1. Excuse me. Now to calculate its expectation, this is fairly easy. Since it can take only two possible values, expectation x will be what? 0 into 1 minus p plus 1 into p. Directly using first principles, only two possible values are there. 0 into the probability of it taking the value 0 plus 1. This will simplify to nothing but p. Similarly, expectation x square. This will be 0 square into 1 minus p plus 1 square into p, which again is nothing but p. So my variance x is nothing but expectation x square minus expectation x whole square, which will be p minus p square, which can be written as p into 1 minus p. Just keep one thing in mind. Frequently, we will be denoting 1 minus p in terms of q. We denote 1 minus p in terms of q, so this can be written simply as pq. Again, write a note. A Bernoulli variable is also called an indicator variable as its value can be used as its value can be used to indicate whether or not some specified event has occurred. Some specified event has occurred. Now we would be closely looking at binomial, geometric, negative binomial. All of these can be thought to be ultimately starting from a Bernoulli trial. We will shortly look, there is a relation between a Bernoulli distribution and binomial. Similarly, there is a relation between geometric distribution and negative binomial distribution. And all of these, the six distributions, how six? Bernoulli, geometric two types, which makes it a total three, binomial, and then again negative binomial, which are of two types. All of these six are ultimately, let's say, starting from a Bernoulli trial only. So that was the reason why I specifically made a write about a Bernoulli trial, because when we want to understand geometric as well as, let's say, a negative binomial distribution, they all will be starting from a Bernoulli trial itself. So next, give the heading geometric type 1. Geometric type 1. So here, as you know, we were dealing previously in a Bernoulli trial. X was being modeled as total number of success in one trial. Geometric type 1, a Bernoulli trial are being repeated. What we are looking at is the trial on which we get our first success. The trial on which we get our first success. So say, I will be repeating, this is just for understanding right now. So the way to write it is X follows geometric P. And note that this P was nothing but my probability of success only, the way which we have defined it previously. So now write down this first. Consider a number of sequence of rather consider a sequence of independent and identical Bernoulli trials where probability of success is P. Where probability of success is P. Full stop. Next line, or you can continue saying the random variable of interest. The random variable of interest is the trial on which we get our first success. Within brackets, or the number of trials that has been, or the number of trials that has to be performed to get first success. So how we can visualize it is X is basically the trial on which we get our first success. Now, can you tell me logically what should be the probability? X is equal to small x. That is, we are getting our first success on which trial? On the xth trial. So what should have happened in the first x minus 1 trials? Failures. All the first x minus 1 trials should have failures and the xth trial should have a success. So the probability will be 1 minus p whole to the power x minus 1. This is nothing but basically probability of failures in the first x minus 1th trial. And on the xth trial, I get nothing but a probability of success, which is nothing but p. Now just tell me, if I am looking for my first success, what is the minimum number of trials I need to conduct? 1. To get first success, I need to at least conduct the trial at least once. So x can take the values 1, 2, 3, so on till infinite. Please see that whether you are being able to understand the structure of distribution, how we are getting it, because these are logical. You should be able to get it. Ultimately, there is no need to memorize. You have actual tables, but the essence is being able to appreciate how this particular distribution can come up when modeling any activity in our day-to-day life, or whether it's for an insurance company. Once attending the online class, just confirm me if this particular part is clear by typing a yes. I'll proceed further then. Perfect then. Next, what we are going to look forward to is calculating its expectation and variance. So expectation x will be summation x into probability x equal to x, and keep in mind here limits are from 1 to infinite. So now let me try to let's say expand it. When x takes the value 1, what is probability x equal to 1? It will come out to be nothing but p. First term will be 1 into p. The next term will be 2 into p into 1 minus p. Next term will come out as 3p square, 1 minus p, and so on. Sorry, this shall be 1 minus p whole square. Next term similarly will be, let's say, 4p, 1 minus p whole cube, and so on. So let me take p to be common. What I'm left with is 1 plus, can I write this as 2q, 3q square, so on, where q is nothing but 1 minus p. So now if you will observe, the structure which we have inside bracket is basically a form of arithmetic geometric progression, where the coefficients are increasing in an arithmetic way, 1, 2, 3, 4, and then the powers of q starting from 0, then 1, then 2, then 3, so on. So there are different ways to deal with an AGP. We will look at, this is a very standard format, and we will memorize the result going forward. Before that, I will show you all the derivation as well, how to go about dealing with this particular term. So let A be equal to 1 plus 2q plus 3q square, so on. So the way to deal with this, just take a look and then take down the notes later on. I multiply both sides with q. So this will be what? Q plus 2q square, so on. I've just left a space here purposely. 1 into q is q, 2q into q is nothing but 2q square, and so on. Now if I will subtract a minus aq, now we compare the terms having common powers of q. 1, 2q minus q, 3q square minus 2q square, and so on. So I hope you must have recognized the pattern. It's going to be 1 plus q square plus q cube, so on. So what I'm left here is a into 1 minus q, and on the RHS, this is nothing but a geometric progression, infinite GP, where the first term is 1 and the common ratio is q. So we know that the sum of an infinite GP is nothing but a divided by 1 minus r, with the condition that the common ratio, the modulus of that must be less than 1. Now q, what is q? It is 1 minus p. Right. What is P? P lies between 0 to 1. So Q also lies between 0 to 1. So automatically that my condition is also satisfied. So this will be 1 divided by 1 minus Q. So what am I getting A? Or I can write this as 1 minus Q whole to the power minus 2. See if the steps are clear to you or not. Now again, let me just continue. Now here I got A as 1 minus Q whole to the power minus 2. What is 1 minus Q? Or your expectation x, I can write as p into 1 minus q to the power minus 2, which I can write as p1 minus q whole square. 1 minus q is nothing but p. So this is p by p square, which is nothing but 1 by p. Now all of you take this down and see whether each and every step is clear or not. This was covered now, first class. So again, this particular result, you know, that the expansion of 1 minus q whole to the power minus 2 is 1 plus 2q plus 3 square, so on, is something which we had covered in the first prerequisite class, right? Now let us try to attempt finding expectation x square, which is going to be a little bit more difficult. Also keep in mind, you know, there is a direct formula for an AGP. I'll be sharing that in the group later itself, or you know, you could directly Google as well. We can directly find the summation of a AGP. Here we are seeing that the progression is in the form of 1, 2, 3, 4, so on. We can have certain cases where the progression is of a different format. So for all these cases, there is a specific formula for an AGP as well, which you could directly use. Again, in examination, if they ask you to derive, then it is expected that you must be following steps. Then the standard formula for summation of an AGP, I don't think so you should be able to use it because it's not a standard result given in our syllabus as such. So now let us try to attempt to find expectation of x square. So this will be again summation x square, probability x equal to x running to 1 to infinite. My first term here is going to be again p. Next term will be 4pq. Next term, if you will see, will be 9pq square, then 16pq cube, and so on. This I can write as p1 plus 4q plus 9q square, so on. So now let A equal to 1 plus 4q plus 9q square and so on. So again, standard technique is first I will multiply q, right? And next what I get is q plus 4q square and so on. Take a look at the screen itself, then you can copy it down. Now if I subtract, what I will get is a minus aq is 1 plus what will be the next term? Then, so now if you observe, coefficients are going to be 1, 3, 5, 7, 9, 11, all the odd numbers, and q power will be 0, 1, 2, 3, 4, so on. Now here again, this is not a very direct format, but if you will see, I can write this as 1 plus q square, so on, and in the same step, plus 2q plus 4q square, so 3q can be broken into q plus 2q, 5q square I can break it into q square plus 4q square and so on. So next, on LHS I have a into 1 minus q. On RHS, if you will take a look at the first line, this will be nothing but what, 1 by 1 minus q, right? And the second term, the first line will be nothing but 1 by 1 minus q, and second, if I take 2q common, I will be left with 1 plus 2q, 3q square, so on, which again is nothing but a recognizable format. So this will be 1 by 1 minus q. This is nothing but the term inside bracket is nothing but 1 minus q whole to the power minus 2, something which we just used while calculating expectation x. So now if I take common, this will be 1 minus q plus 2q by 1 minus q whole square. So this will come out to be 1 plus q by 1 minus q whole square. And so my a will come out to be 1 plus q by 1 minus q whole cube. 1 minus q goes on the other side. So again, let me just complete this. So now expectation x square will come out to be what? P into 1 plus q divided by 1 minus q whole cube. This can be written as P. 1 plus q, I can write it as 1 plus 1 minus P. In denominator, this is nothing but P cube. So what I'm left with is 2 minus P by P square. And now if I calculate the variance, this will be 2 minus P by P square minus 1 by P square, which will come out to be 1 minus P by P square, which I can also write as Q by P square. So this is the result which we have. Note this down, see if you are comfortable with all the steps or not. So this was geometric type 1. Closely related to this is geometric type 2, where what we are looking for is the number of failures before our first success. In type 1, we were looking number of trials required to get our first success, or the trial in which we will get our first success. Type 2 is number of failures before first success, or the number of trials which we need to conduct before we get our first success. So now in geometric type 2, again, the way to write it is same. X follows, let's say geometric, you need to write say 2, which denotes type 2, P. Now, to compare, instead of writing X, let me just take it to be Y so that it becomes a bit more easier to compare. If X was my geometric type 1, okay, if X was my geometric type 1, then Y is nothing but X minus 1. How? If X was the trial on which we got our first success, then the number of failures will be X minus 1. If I got the success on the first trial, how many number of failures we saw? 0, 1 minus 1. If we got our first success on the second trial, then how many failures did we see? 1 failure. So Y is nothing but X minus 1. And here probability Y equal to Y will be how many failures? Okay, Y equal to Y. How many failures do I want? Y failures I'm looking for. 1 minus P to the power Y. And then on the next trial, there should be a success as well. And the values which Y can take will be 0, 1, 2, so on. Because we can have 0 failures before our first success. It is comparable from here as well. X was taking which values? 1 to infinite. Therefore, what values can Y take? 0, 1, 2, 3, again, so on till infinite. See, in certain questions where it is mentioned, use geometric type 1, type 2, so on, fine, very simple. In certain cases where these things are not mentioned, there you need to apply this logic, how exactly we came up with a, say, a Bernoulli distribution or a geometric type 1 distribution or a geometric type 2 distribution, so that you know which one needs to be used. Number of trials on which we'll get our first success. I need to conduct at least one trial to get a success. So logically, that is why X will start from the values 1. Here we are looking for number of failures before first success. So one could have 0 failure before their first success. Now again here when we need to find its expectation, the usual structure will come and AGP will be coming. So I'm not going into derivation, but because it will be of similar format. What I can directly show you is expectation y should be nothing but expectation of x minus 1, because y is nothing but x minus 1. Expectation x minus 1. Expectation x was nothing but 1 by p minus 1, and this comes out to be 1 minus p by p, which I can also write as q by p. And variance y is nothing but variance of x minus 1, which will be again nothing but variance of x only. So remember, variance of geometric type 1 and type 2 both are same only. And you could derive this first results, do give it a shot after the class as well. It will be on similar lines the way we did it for type 1 only. So this was regarding geometric type 2. Your application should be, if you want to, let's say, calculate the amount of money you will have to spend as your examination fee before you pass the paper for the first time. So you can model this as what? Assuming that the examination fee remains constant, examination fee per exam into number of failures. And say assuming like a more practical example would be when you're working, most of the companies who have an actuarial study policy, they tend to reimburse you when you clear the exam. So how much fees do you need to pay from your own pocket as long as you fail a particular exam? So if I want to model this, this can be modeled not directly but indirectly in the form of geometric type 2, where the values won't be 0, 1 and 2. It will be, let's say, what if say 20,000 is the cost of one exam, so the values will be what 20,000, 40,000, 60,000, so on. So I can model it as 20,000 y, where y is the number of attempts or the number of failures basically before a first success, and this will give me nothing but the amount which you need to pay from your own pocket. So questions would be like this: directly maybe you can't use a particular distribution, you need to say modify it, 20,000 say into y. Next, binomial. Now a binomial trial distribution, anything, we are looking at binomial distribution. If I repeat the Bernoulli trial n times, what I come up with is with nothing but a binomial trial. That is repeating the same experiment n times where all of them are identical. That is, the probability of success or failure remains the same in each trial, and the results of each trial are independent with each other. So right now, binomial distribution, and in that, first the way to denote it is we have two parameters over here. One is n and another is again p. Note that p by default is nothing but probability. Also keep in mind, this is the usual standard way to denote it is examination. They can also denote as x follows binomial, say m comma q. So now don't get confused. Here q is nothing but probability of success. The parameter which is given here is nothing but the probability of success. And m becomes the number of trials. Here n is the number of trials. Here it is being denoted by m. So my whole point is that don't get fixated to n and p. The first parameter, whatever way it's denoted, is the number of trial. I can denote it as a, b, c, d, e, f, g, anything. and the second one is the probability of success. Usually we represent by P. In certain questions, they might represent this by Q or any other thing as well. The reason why I am highlighting Q is because we generally start with P over here. Then I'm denoting Q as what? 1 minus P. So don't get confused. If they're writing over Q here, it means it is 1 minus P. That is not the case. So now write down, give a note and write. If we perform the same Bernoulli trial, if we perform the same Bernoulli trial n times, small n, with all trials being independent, with all trials being independent, then this entire performance of trials, together forms the binomial distribution. Forms the binomial distribution. So how can I denote X? The total number of success. A better way of writing would be total number of success. So now let's say if we're conducting an experiment n times, then what does X give us? The total number of success. So now if I want to find this probability X equal to X, how many trials have I conducted? N trials. How many success am I looking for? X. What is the probability of one success? P. So what is the probability of X success? P to the power X, and the remaining needs to be failures. 1 minus P to the power N minus X. And we can arrange this failure and success in how many ways? NCX ways. We want, let's say n takes the value 10. What is the probability that I have 6 success in 10 trials? So P to the power 6, Q to the power 4. And in how many ways can I order this success and failure? What do I say by order? I can have, let's say, success, 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 failure, 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 failure. Another way is S, 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 F, 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 S. And there are tons of other ways. So total number of ways to, arrange the number of success and failures is 10C6. So this becomes, can you all tell me what possible values can X take? How many success can we have in n trials? What is the lowest number of success? 0. And highest? 6. No, matlab n. If we are conducting n times n, so X can take the value 0, 1, 2, so on till n. Remember, whenever there is an upper limit, you need to write the last value as well. If you just write dot dot dot, it means it goes till infinite.
Is the difference between Bernoulli trial and in Bernoulli there are infinite trials?
No, Bernoulli, one trial only takes the value 0 or 1. Geometric, it's different. You can't compare over here. Geometric, we're looking for the trial in which we get our first success. Binomial, we are looking at total number of success in n trials. So in binomial or Bernoulli, number of trials is fixed. In geometric, number of trials is not fixed. We are looking at the trial in which we will get either our first success or first failure. You can model it, yes. I can model it as you appeared for the exam 10 times. In how many times did you clear it? Assuming that probability of clearing each exam remains same and the results of each exams are independent, then this can be modeled as binomial. So binomial basically holds that you're performing the same experiment again and again and probability remains the same only. And again, statistically speaking, results should be independent of each other. Flipping a coin, rolling a die, wherein I define my success to be getting a 6. So my probability of success becomes 1 by 6, probability of failure becomes 5 by 6. I want to find in how many throws did we get a 6. If I threw the dice 10 times. So I can model this as a binomial distribution. So again, our starting point is Bernoulli, 2 outcomes of one time. Now if I want to repeat this n number of times, I can model this as binomial distribution. So, let's say if you want to take an example, have you all watched Friends series? Okay, so in that series, okay, there was a particular scene where a particular person named Monica had to put a $1 in the coin whenever she shouted, okay, while work. So let's say, and for the analysis, I need to count the number of days on which Monica put a $1 coin in the particular jar in the next 10 days. So I can model this as a binomial distribution where let's say the probability of success, you can model right now it is not success, but the probability of Monica putting a $1 coin over jar is P, right? So either she puts a coin or she does not puts a coin. Probability of putting a coin is P. I am modeling it for 10 days. I need to model on how many days did she put $1 in the jar. So this can take the value what? 0, 1, 2, 3, so on till 10. And I can model this as a binomial distribution. So my starting point is key on a single trial. There needs to be 2 outcomes. Again, keep in mind, originally a particular experiment can have more than 2 outcomes. When you throw a die, you can get a 1, 2, 3, 4, 5, 6. If I define my success to be getting a 6, in that case, there are 2 things, either a success or a failure. The success event only has a 6, the failure event has 1, 2, 3, 4, 5. So I can model this as what? A Bernoulli trial. And then if I repeat this again and again, I come up with a binomial distribution. So this was just not to fixate your mind, Bernoulli needs to have 2 outcomes only. You can have more than 2 outcomes, but the way you will define the events, ultimately will be left with 2 events only. One we refer to as success, the other we refer to as the failure. And now we would be, shortly taking a comparison, how starting from Bernoulli, I can end up in a binomial. So before that, let us try to find the expectation. And before that, we need to use this particular result. If you all would remember, adding up the probabilities will always give us 1. The summation of a probability function or integration of a PDF always gives us 1. Here we are dealing with discrete distributions. So logically as well as mathematically, that is the result, summation NCX P to the power X Q to the power N minus X, where X runs from 0 to N, is nothing but 1. This is using the logic that probabilities, all of them must add up to give us 1. Mathematically, see this. Remember that A plus B to the power N, A plus B to the power N can be written as summation NCX A to the power X, B to the power N minus X, X running from 0 to N. Again, this is something I guess I might have covered in the first class. Can we just check whether this was mentioned or not in the first prerequisite class? Binomial expansion under the heading. One of you has mentioned, see, it might have been covered, expansion of A plus B whole to the power N. It's there, right? So now See, logically we showed that the summation of this must be 1. Now mathematically also let me show you. Summation of this particular term is nothing but p plus q to the power n. Summation ncx p to the power x q to the power n minus x. This is nothing but the binomial expansion of what? P plus q whole to the power n. And what is p plus q? 1. P plus q is nothing but 1. 1 raised to the power n is nothing but 1. So mathematically also we are getting 1 over here. So again, this is there given the result in the prerequisite class. So no need to mention. We would be using this property going forward. So if I want to find expectation x, expectation x will be x ncx p to the power x q to the power n minus x, where x runs from 0 to n. Again, take a look. First term, when I put x as 0, 0 into anything is 0. So I can also write this as summation x running from 1 to n x. Now I'm splitting ncx. I can write this as n factorial x factorial n minus x factorial p to the power x q to the power n minus x. Now, if you will remember, x factorial can be written as x into x minus 1 factorial. So this x factorial is x into x minus 1 factorial. X and x will get cancelled out. I'll be left with what? N factorial by x minus 1 factorial n minus x factorial p to the power x q to the power n minus x. Now see what I'm trying to do. N factorial. I can also split n factorial as n into, and I will also explain why I'm particularly doing this manipulation here. N factorial I can write as n into n minus 1 factorial. Summation is with respect to what? X. N is independent of that. I will take out a n common and a p common. Inside I will be left with n minus 1 factorial x minus 1 factorial n minus x factorial. This will be p to the power x minus 1 q to the power n minus x. X runs from 1 to n. We will see why I have taken np outside. Now let y equal to x minus 1. Let y equal to x minus 1. So can I write this summation as np? X was taking value from 1 to n. Y is from x minus 1. So what possible values can y take? 0 till n minus 1. When x takes the value 1, y will take the value 0. When x takes the value n, y will take the value n minus 1. So this will be y running from 0 to n minus 1. N minus 1 factorial. In denominator, x minus 1 is nothing but y factorial. And this will be n minus y. N minus 1 minus y factorial. This will be p to the power y, and this will be q to the power n minus y plus 1 actually. X minus 1, x is y minus 1, and this will also be n plus 1 minus y. N minus x, x is y minus 1, n minus y plus 1. Okay, that's correct. We are getting this form. I have just replaced x with nothing but y plus 1. Okay, this will be minus 1. I have replaced x with nothing but y plus 1 over here. And now if you will see, summation y running from 0 to n minus 1. This term is nothing but n minus 1 cy. You can go back and see. If I start from n minus y cy, n minus 1 factorial, denominator y factorial, and n minus 1 minus y factorial. P to the power y. I have written down this step. Start from here. N minus 1 cy. This will be n minus 1 factorial. In denominator y factorial and n minus 1 minus y factorial. So this is nothing but 1. How 1? P plus q to the power n minus 1. Take a look at this. The inside summation is nothing but p plus q whole to the power n minus 1. When we had n, this was n, this was n, this was n minus y. Now instead of n everywhere I have n minus 1, n minus 1, n minus 1. And p plus q is nothing but 1. So what we're left with is nothing but np. So here we have used this particular result, that summation x running from 0 to n. Now keep that this is in form of n. If you have n minus 1, n minus 2, you need to modify it accordingly to be able to use this particular result. So we end up with what? N into p, which is nothing but the mean. We will later see there are far easier ways to calculate mean of a binomial distribution, but this was the method using first principle. So take this down and let me know if the steps are clear to you or not. Calculation of expectation x square will be far more complicated compared to calculation of expectation x. So this was regarding expectation x. For variance, we will take a look at the other way. Note that in there are, let's say, three ways I would say. One way is using first principles. Second way is, say, for binomial specific or any other distribution, I can express binomial in terms of Bernoulli. So from there also I can calculate the mean or the variance. Next, when we would be covering chapter number 3, which is generating functions, from there we will see another techniques as to how to calculate the mean and the variance. In most of the cases, the first principle is going to be pretty lengthy, but you should be comfortable with that in case they might ask you some different type of question. Other than that, if they simply ask you to derive something without stating first principle, you could use any technique. Okay, you want me to repeat the step. So let y equal to x minus 1. So my x, if y is equal to x minus 1, then x is nothing but y plus 1. So everywhere I will replace x with a y plus 1. So here x I replace with y plus 1 becomes y factorial. Here if I replace x with y plus 1, I am left with n minus of 1 minus y. P to the power x minus 1 becomes p to the power y. Q to the power n minus x becomes q to the power n minus y minus 1. Limits: when x takes the value 1, y takes the value 0. So 0. When x takes the value n, y takes the value n minus 1. And we come up with this term, which again, as I explained, can be represented in this particular format. And this is nothing but the binomial expansion of p plus q whole to the power n minus 1. So now I can represent a binomial random variable. Say if x, now here I am saying x is following binomial n comma p, and say y follows Bernoulli p, then I can express x as nothing but y1 plus y2 plus y3 yn. And you can think this logically. If I need to find the total number of success in n trials, first I will see what I got in the first trial. Then I will add whether I'm getting a success on the second trial or not, and so on. So a binomial distribution can be represented as a series of independent and identical Bernoulli trials. What do I mean by independent? Outcome of one does not influence other. What do I mean by identical? All of them must follow Bernoulli with same parameter. Note that a Bernoulli 0.2 plus Bernoulli 0.3, this will not give a binomial. If both of them have the same parameter and both of them are independent as well, then only will I get binomial. So remember the usage of term independent and identical. So take this now, give a note and write. Binomial distribution can be viewed as or can be expressed as summation of n independent and identical Bernoulli trials. Now we will see how in a single step we can find both the mean as well as variance. So can I write expectation x? All of these are independent. So I can write this as, even if they weren't independent, I could have still broken down this. And all of them are identical. So all of them will be p plus p. How many times? N times. NP. Variance x, variance of y1 plus y2 yn. Because all of them are independent, I can write this as variance of y1, variance of y2, variance of yn. This will be pq plus pq plus pq. How many times? N times, which becomes npq. Take one task as a homework. Try to find expectation x square for binomial distribution using first principle. Try finding expectation x square for a binomial distribution using first principle. Give some time yourself. If not, again, feel free to Google it out. I mean, you will directly find answer there. My point is you are being able to understand all the steps involved. So first, give some time. Try to attempt it yourself. If you're not getting it, not being able to progress, can take the help of Google. You will directly find the solution. Just see if you are being able to understand all the steps or not. And I can tell you the result. we know that expectation x square is nothing but variance x plus expectation x whole square. So npq plus this is going to be, and if I take an np common, I will be left with you will get something of this form, or you can just leave it till here. This is what your expectation x square should be coming out to be. So this was regarding binomial distribution. Next, we'll look at negative binomial. Type 1. So here the parameters are a k and a p. So how do we define x over here? The number of trial on which we get the kth success. In geometric, what we were looking at, trial on which we got our first success. Here, the trial on which we are getting our kth success. Again, keep one thing in mind. Bernoulli is nothing but a special case of binomial. If I put the value of n as 1, binomial 1 comma p is nothing but Bernoulli. If I just put n as 1, so x is nothing but y1, so my binomial becomes nothing but Bernoulli. So Bernoulli you can view as a more special case of binomial when n is 1. Similarly, geometric is nothing but a special case of negative binomial when k is equal to 1. So here number of trial on which we got our kth success. Now let us try to see. First I will take an example to let you all show the structure. If I say that I got my sixth success, if I got my sixth success on 10th trial, then can we say that in the first n trials we had 5 success and 4 failures? It can be arranged in any order, and on the 10th trial I got my sixth success. So can I write in the first n trials there are 5 success, 4 failures. Total ways to arrange them is 9c5, 9c4. You can write anyway 9c5, p to the power 5, q to the power 4. This is the first 9 trials, and then on the 10th trial you are getting a success. So this probability makes sense. This is the probability of getting sixth success on the 10th trial. Note that we are we are applying combination only on the first 10 trials because the 10th one is fixed. It needs to be success. The first 9 we have 5 success, 4 failures which we need to arrange. So probability x equal to x. Now let us try to construct the general form. On the xth trial we are getting the kth success. So how many success will we have till x minus 1 trials? K minus 1. So x minus 1 c, k minus 1, p to the power k minus 1, and then there's another p as well, and q to the power. This will be number of failures, which is x minus 1 minus k minus 1, or directly I can write as x minus k. If on the xth trial I get the k success, then my total failure is x minus k. And now, can you tell me what possible values can x take? Think about it. How many minimum trials do I need for k success? Minimum k trials. If I'm asking you how many trials we need for the sixth success, you need to at least have performed the trials 6 times. So x can take the values k, k plus 1, so on. Is it clear? Now again, take an assignment, try finding the mean using first principle. Try finding the mean of negative binomial type 1 using first principle. Now, that is an assignment. We'll talk about that later. Coming to an easier way, we can express negative binomial type 1 in terms of geometric type 1. How? Here, what we are looking for, the trial on which we got our kth success. Or let us take this example, 6th success. What I can do is first find the trial on which I got my first success. Then find the additional number of trials on which I got my second success. Then additional trials on which I got my third success, so on. If I add all them up, I will basically get the trial on which I'm getting my 10th success. Say for example, I got my first success in the first trial. I got my second success. Additional how many trials? Say one, third, two, fourth, three, fifth, say three, no, two, and sixth on first. If I'll add all of them, 1, 2, 4, 7, 9, 10. What I'm getting is that on the 10th trial, starting from the beginning, I got my sixth success. So the sequence is in this form. My first trial was a success, second trial was a success, third was a failure, fourth was a success, fifth was a failure, sixth was a failure, seventh was a success, again a failure, success, success. First success, one. Additional trial for second success, again one. Additional trial for third success, 2. Additional trial for fourth success, 1, 2, 3. So I can express x as y1 plus y2, so on, yk, where y follows geometric type 1 p. Just like we were able to express binomial in terms of addition of independent and identical negative Bernoulli trials, similarly, I can express negative binomial as the addition of independent and identical geometric random variable. Now from here, we can see that expectation x. We add all its expectation, which will come out to be k by p. Similarly, if I want to find variance, I will add variance of all of them, which will come out to be kq by p square. Next, give the heading negative binomial type 2. Now, by observation, can you tell me what should this look like? As in type 1, what was x? Number of trials on which we got the kth success.
Failures. Number of trials in which
Right? Like geometric type 1, number of trials on which we got our first success. Type 2 was number of failures before first success.
number of failures before KX.
Before kth success, right? So negative binomial type 2. The way to write it is x follows NBIN type 2. Again, parameters are k, comma p. And here I can define x to be number of failures before kth success. Again, let us take an example. Say I want 2 failures before 6th success. I want 2 failures before 6th success. So first of all, can you tell me how many trials would be there required? We want 2 failures before 6th success. So total trials will be 8. 2 failures, 6 success. And then the 6th success will be on the 8th trial. If I want probability of 2 failures before 6 success, it means that 1, 2, 3, 4, 5, 6, 7, 8. The last one needs to be a success. In the first 7, I can arrange them in how many ways? 5C 2 ways. There are 5 success, 2 failures, right? No, sorry, 7C2. 7C2 ways. 7C2, 7C5, both the same thing. Then P to the power 5, Q to the power 2, and then this probability will be again P. So here X is the trial on which we are getting our X is the number of failures before the kth success. So in the first k minus 1 trials, I will be looking for X failures. In the first k sorry, no, not k. K plus X C X. If there are k success and X failures, total tries will be k plus X, right? But we need to subtract the minus 1, right? You can compare here 2 failures, 6 success. We were getting 8 trials. This was 8 minus 1. Concept is how many failures we are looking at? Total X failures and success k minus 1. So k plus X minus 1 Cx. P to the power, how many success? K, Q to the power X. And now tell me what values can X take? Logically think about it. Number of failures before kth success. We can have 0 failures, 1 failure, 2 failures, so. And if you just compare over here, if X is negative binomial type 2 and say Z supposedly is negative binomial type 1, then X is nothing but Z minus K. If on the xth trial I'm getting the kth success, if on the let's say the zth trial I'm getting the kth success, if I'll subtract that minus k, number of trials minus number of success is nothing but the number of failures. Like there we had X was y minus 1, here Z minus k. You can just visualize if on the 10th trial I got my 6th success, then the number of failures before 6 success is 4, which is 10 minus 6, Z minus k. You can write this relation as well. Negative binomial type 2 is negative binomial type 1 minus k. Yes. We can have infinite failures before kth success. And now again here we can express X to be number of failures before first success plus additional number of failures before second success, so on. So you can express negative binomial type 2 as summation of independent and identical geometric type 2 random variables. And from there I can find expectation X. This will be nothing but KQ by P. Variance X will be nothing but KQ by P squared. And if you'll observe one thing for negative binomial type 2, if you'll compare the mean and variance, can you all tell me which one will be always greater than the other? For negative binomial type 2. No. You see the mean and variance. Between this, which one will be greater? Because denominator has additional p, but p takes the value. So if in denominator we have 0 to 1, so the value will increase. If I divide any number by a number which is less than 1, any positive number less than 1, the total value will increase. So my variance is always greater than the mean in case of negative binomial type 2 distribution. Can take this as well, might be required. The variance of a negative binomial type 2 distribution is always greater than its mean. When does this help is, if a certain scenario is given where you see that the variance is greater than mean, so you need to see which all distribution allows that. And when you go back home, take a look at that, in among all the distributions we are doing, where does mean is same as variance, or where mean will be always greater. In some places it could be anything, it could be greater than, it could be less than as well. So just for example, let's say if I talk about let me talk about geometric first, Bernoulli first of all. Mean is P, variance is PQ. So variance is less than mean because Q is what, between 0 to 1. So PQ will be less than P only. Next, I have geometric, the mean of which is 1 by P and variance is Q by P square. We can't comment as such. Because mean is 1 by p, this is q by p square, you won't be able to comment what is the case. It depends on the values of q and p. So variance is nothing but mean into q by p. If q is greater than p, then my variance will be, let's say, higher. And if it is less than 1, if q is less than p, in that case my mean will be higher. Let me express this. Q by p square is the variance, which can be written as 1 by p into q by p, right? This is the mean, this is the variance. It can be q is greater than p, it can be q is less than p. For example, if p is 0.4, then q is 0.6. So this ratio is more than 1, therefore variance is greater than mean. But if let's say p is 0.6 and q is 0.4, in that case, the variance is less than mean. So we can't say. In binomial distribution, what was the mean? Mean was NP. Mean was NP. Variance was NPQ, which is always less than NP. So this will be required because we would ideally want my variance to be more than mean. So of all the distributions we have covered so far, negative binomial type 2 fits the case. As for type 1, k by p, kq by p square, we again can't comment as such. So it's only for type 2, whether it's geometric type 2 or negative binomial type 2, where what is going to happen is my variance is always be going to greater than mean. Now, next is Poisson distribution. Poisson distribution. Now, if you would again check in the first prerequisite class, we had covered that e to the power x is 1 plus x square by 2 factorial, so on, or basically summation x to the power k by k factorial, k running from 0 to infinite. So now, if I multiply both the sides with e to the power minus x, will I get a 1 on the LHS? And here I'll get e to the power minus x to the power k, a factorial. All these things are adding up to give us what? 1 now. Any sort of function which adds up for its entire range to give us 1 can be used as a probability function, right? So this is, you could think this to be the motivation of this distribution where x follows Poisson lambda. Note that this parameter must be always greater than 0 and my probability x equal to x. Now keep in mind, whatever distributions we did, the probability was very obvious. Here there is no intuitive meaning. You know why this probability is coming. It's just that we can express in this form. probability x equal to x is e to the power minus lambda, lambda to the power x by x factorial. This is my probability function for a Poisson distribution. And what is the range? From 0 till infinite in multiples of 1. Now here we will find the mean and the variance. We will see both of them are coming to be lambda only. So first thing, finding the mean. Expectation x, summation x, and just probability x equal to x, x running from 0 to infinite. Can I write this as summation? Let's say, would I want to do that? I can write this from x running 1 to infinite, x into probability x equal to x. Because when x is 0, the first term will be 0 only. Summation is from 0 to infinite. When I put 0, x is 0. So again, take a look, then note it down. This will be x into e to the power minus lambda, lambda to the power x by x factorial. And x is from 1 to infinite. Can I write this as summation x running from 1 to infinite? E to the power minus lambda, lambda to the power x by x minus. If I take a lambda outside, e to the power minus lambda, lambda to the power x minus 1, x minus 1 factorial, x running from 1 to infinite, which I can write as lambda summation y running from 0 to infinite, e to the power minus lambda, lambda to the power y by y factorial. Summation of this is nothing but 1. So we are left with lambda. Expectation x comes out to be lambda. Take this down, see if it's clear or not using this particular result. In this step. I will take it down. Next, let us try to find its variance. First, we need to find expectation x square. And then we will see there is another easier way to find its variance. But let us first find expectation x square, which will be summation x square, probability x equal to x, x running from 0 to infinite, which I can write as x running from 1 to infinite, x square e to the power minus lambda, lambda to the power x by x factorial, x running from 1 to infinite. This will be x e to the power minus lambda, lambda to the power x by, let's say, x minus 1 factorial. Now, let me attempt to expand it. When I put the value of x as 1, 0 factorial, remember, is nothing but 1. 0 factorial is 1. So what I'm left with is lambda e to the power minus lambda. When I put x as 2, 2 by 1 factorial, which is 2. So I have 2 lambda square e to the power minus lambda. Next, what I have is 3 by 2 factorial, which is again nothing but, no, it will be 3 only. 3 uh, so on, right? Now I will take lambda e to the power minus lambda common. 1 plus 2 lambda plus 3 lambda by 2 factorial. Next term, can you say it will be 4 lambda by 1 plus 2 lambda plus 3 lambda square, 4 lambda cube. Yes. I've taken it outside. Acha, here. Clear so far? Lambda e to the power minus lambda we have taken out common. Now let us see what to do with this. I can write this as lambda e to the power minus lambda 1 plus lambda one plus 2 lambda, sorry, 1 plus 2 lambda uh, split by factorial में I have split it down there itself x square by x factorial. Wait, this might be a bit difficult to identify. Let me do it in this form. That won't help. I'm doing something else. Wait. This I can expand, and the first term will be lambda e to the power minus lambda plus, when I put x as 2, 4 lambda square e to the power minus lambda by 2 factorial plus 9 lambda cube e to the power minus lambda by 3 factorial, so on. Lambda e to the power minus lambda common 1 plus, this will come out to be 4 lambda by 2 factorial plus 9 lambda square by 3 factorial, so on. Now, I can write this as 1. This is nothing but 2 lambda. 1 plus 2 lambda. 1 plus lambda, lambda square. Okay. 1 plus 2 lambda. I can write this as 1 plus lambda. Let me simplify it. Go step by step. 1 plus 2 lambda plus 3 lambda square by 2 factorial. It's back to the same thing only actually. So now in the next step, I will write 1 plus lambda square by 2 factorial plus lambda cube by 3 factorial, so on, plus I had a 1 there, I have 2 lambda plus lambda 2 lambda square by 2 factorial. I had 3 lambda square by 2 factorial, so I need to add 2 lambda square by 2 factorial. Similarly, next term, what I will be having is 4 lambda cube. So this is lambda cube, this will be 3 lambda cube by 3 factorial, so on. This is one single step. So now lambda e to the power minus lambda 1 plus lambda square by 2 factorial, so on, is nothing but e to the power lambda. And this term, if I take a lambda common, this will be 1 plus lambda square by 2 factorial, so on. Lambda e to the power minus lambda e to the power lambda plus lambda e to the power lambda, which will come out to be lambda plus lambda square. E to the power minus lambda will cancel out to give us 1. So this was expectation x square, therefore variance x is ex square minus ex whole square. This can be used if I want to model a let's say a data set which has same mean and same variance using a discrete distribution. So your first thing which should come to your mind is using a Poisson distribution because its mean and its variance are theoretically the same. So we take a look at the steps involved. Next, what we have is a hypergeometric distribution. Again, that is something we do not need to cover explicitly in detail as such because its derivation of mean and variance is not as a part of the syllabus. So directly that is something to take a look from the material itself. And just to give an example of Poisson distribution, where it is used. Whenever the question mentions that a particular thing can happen at a constant rate. If I say students are arriving at a constant rate of 5 per hour, students are arriving at a constant rate of 5 per hour. Calculate the probability of 3 students arriving in 1 hour. It means you need to use a Poisson distribution. Whenever there is a constant rate, it implies that you need to use a Poisson distribution. Hypergeometry you can write, refer to material itself. It's a very short one. Uh, Give the next heading. Recursive relationship. And right now, we would attempt to establish, we would attempt to establish a general relationship, a general relationship between probability x equal to x given on the screen and probability x equal to x minus 1. So let me take an example of Poisson to show you what I'm trying to do. Probability x equal to x is e to the power minus lambda, lambda to the power x by x factorial. Can I write this e to the power minus lambda, lambda to the power x minus 1 by x minus 1 factorial into lambda by x? This is nothing but lambda by x into probability This helps in numerical calculation. When you want to calculate, say, probabilities, instead of using tables, inputting this again and again for different values of x, you can start with a one value, and then using this relation, you can continue to calculate other values. For example, first you will calculate probability x equal to 0, which is, say, e to the power minus lambda. This is there in your calculator. If I want probability x equal to 1, this will be lambda by 1 into this particular term. Let's say this was the previous answer A. So in your calculator, what you can do is answer button into lambda. Then if I want probability x equal to 2, the answer which you have stored, let's say which is B, you can multiply what? Lambda by 2 into B. So this basically helps you to perform calculations in a much more efficient way. Apart from that, in examination, they might ask you express in a particular form. So this is the structure. Again, take it as a task. Try this out for binomial and negative binomial type 1. Attempt to establish such relationship for a binomial distribution and negative binomial type 1. So this is all we have under discrete distributions. Finally, to conclude our class, we'll be taking a look at the actuarial tables, just to see what all data do we have for these discrete distributions. So now if we'll take a look, starting from page number 6, we have first of all binomial distribution. Again, just keep in mind, another way of writing NCX is the way they have written. NX in the same line, that's another way. Then you also have moments, variance, coefficient of skewness, so on. Then we have Bernoulli, Poisson, negative binomial type 1, negative binomial type 2, geometric they have mentioned. These are nothing but special cases of negative binomial where k takes the value 1. Then we have uniform discrete. So we have covered all the distributions. Now, apart from this, we also have the CDF table, that is the less than equal to type probabilities for my Poisson distribution. It's page number 175 is on PDF, not sure if this is what you have. This is a 175, I guess. Page 175 of tables. So here you will see you have x, you have different values of mu. Here mu is basically used for lambda. So you will see less than equal to probabilities are there. Then if we continue in next pages, we have that for different values of mu till 25. And then next, if we'll go to page number excuse me, 186, you will have the CDF table for a binomial distribution for different combinations of n and p. So this is just for you to keep in mind whenever you need to find, let's say, less than equal to probabilities, you can directly use tables where the existing combinations of either lambda in case of Poisson or NP in case of binomial is available. So, just for example, if you want probability x less than equal to 7 for a Poisson distribution, so you do not have to separately calculate x equal to 0, 1, 2, 3, 4, 5, 6. You can directly use available from tables itself. And apart from this, yes, binomial, other things are not required. So this is from this chapter so far for discrete distribution. You have the statistical distributions, their results given, and the CDF tables for binomial as well as Poisson. So this is all from my end. Do you all have any doubts? Else I'll wrap up the class. Any doubts with respect to today's class? Don't forget to attempt all the tasks today itself so that we can discuss in tomorrow's class. Fine, I don't see any doubts then. We'll wrap up the class for today. Thanks everyone.